So in the last slide, we said that comparing two groups, the control group and the experimental group, is the name of the game. And we said that we're trying to take some test statistic and to measure the difference between those two groups. But how different is different enough to be significant? Okay, so in other words, how do we know that the difference that we saw in the experiment is not attributable to just chance? Well, the answer is we don't. But we can calculate the probability that it's attributable to chance. And that's what the p-value is. Okay, so the p-value is the following. If you were to repeat the experiment over and over and over again at the same sample size, what percentage of the time would you see results that were at least as extreme as the ones you got in this experiment? And this is all assuming the null hypothesis is true. So let me say that again. Assuming that there is no difference between the groups, right? The control group really is the same population as the experimental group, right? The treatment has no effect. If I were to do the same experiment over and over again, what percentage of the time would I see a difference in the treatment group anyway, just by chance? Okay, and that's what the p-value is. Fine. So more terminology, you need to think about two-sided versus one-sided. So two-sided is if we're measuring something in terms of the absolute value, right? So the p-value is 2 times the probability that x is greater than the absolute value of the measured value. And if the test is one-sided, it's either greater than or less than. And here the notation that we're using is mu, which is the mean, and mu sub 0, which is the mean of the population under the null hypothesis. So this screenshot is taken from a nice applet that you can find online and play with here. But here, if the null hypothesis is that the mean is 325, and we're doing a two-sided test where mu is not equal to 325, we're saying it must be something different than that, either higher or lower, right? And the sample size is 10, and the observed sample mean is 328. Then when you click the Show P button on the applet, what you get is it computes the p-value for you and shows this colored region. And so these colored regions. And so these colored regions, the area under that curve is the p-value. Okay. So that's the probability that it's at least as extreme as the measured value. Okay. And if you get, here the only change I've made is that the sample mean was 329 instead of 328, which means it's even less likely that you would see this by chance. And so the area under those curves is even smaller. And you notice the p-value changed. The p-value went from 0.0574 to 0.0114. Okay. So in order to make some sort of a decision, did this treatment work, right? Do we invest in this treatment? Do we move on to the next stage of trials? We need some sort of a threshold, some sort of a cutoff for the p-value. So what is that cutoff? Well, it's 0.05. Why? No good reason. It makes the math work out. Okay, so this is a 1 in 20 chance. If you can show it's more rare than a 1 in 20 chance, then that's deemed to be good enough. Okay, this is the subject of a lot of controversy depending on what circles what sort of literature you're reading. And we'll talk a little bit more about this in a few segments, but that's all I'm going to say about it right now. So 0.05 is what people are looking for. All right. So now that you're armed with a little bit of basic terminology, let's go back to this first slide from this New Yorker article. And so the question that we raised was, what accounts for this truth wearing off effect? How can we explain what's going on? Okay. So one reason is publication bias. All right, so let me read you a couple of quotes from this article about publication bias. So in the last few years, several meta-analyses, and we'll talk about what a meta-analysis is in a little bit, have reappraised the efficacy and safety of antidepressants and concluded the therapeutic value of these drugs may have been significantly overestimated. Okay. Although and there's other examples in this article as well. Okay, so go back and review the literature and find out that things have been overstated. Why? So although publication bias has been documented in the literature for decades and origins and consequences are debated extensively, there is evidence suggesting that this bias is increasing. All right, so I haven't told you what publication bias is yet, but you may be familiar with the concept, and these are some of the effects. So a case in point in the field of biomedical research and autism spectrum disorder, which suggests that in some areas, negative results are completely absent. All right, so what does that mean? That means that you're only publishing papers that show significant positive gains, right? If we try several treatments and none of them work except for one, we try 20 treatments and only one works, how many papers do we publish? 1, not 20. Okay. So how is this a problem? Okay. So do we have an explanation for this decline effect with publication bias? So how does this actually work? Well, let's make a plot where this study size is on the x-axis. And notice this is log scale, right? So this is 10, and this is 100, and this is 1,000, and so on, right? Well, study size meaning the number of patients, say that are involved in the study. So the bigger the study size, the more statistical power you have, and we'll define what statistical power means precisely in a bit. But the better you are able to determine actual effects, right? And the assumption here is perhaps that, as time goes on and you see some results, you or other researchers are able to garner more money, more funding to do larger and larger studies, right? So this is maybe phase 1, phase 2, phase 3 trials of some new drug. They get bigger and bigger and bigger sets of patients as you get more momentum behind it. And this data is not real. This data is simulated. But imagine you see this kind of decline effect where the results, okay, well, the y-axis. The y-axis is the effect size, and we'll talk about what the effect size is precisely in a little while. But this is the degree of positive outcome, let's say. Right? Let's say negative is bad and positive is good. So this is, the number of smokers you were able to convince to quit with some intervention counseling method, or the number of white blood cells increased as a result of some treatment or so on. Okay. So positive is good. Well, this decline effect, let's imagine, shows this sort of a pattern, right? Where the early studies with just 10 participants is up here, and as the study went up, it sort of got worse and worse and worse. So this is the effect that we see. How do we explain this? Well, this is directly explainable. This kind of an effect would be directly explainable just by publication bias. Right? Imagine that every dot now is a test that was done by some group somewhere for this phenomenon. What you'd expect is this kind of funnel shape where the studies get more and more accurate as you get larger and larger and larger. Right? And they will. With a study, this is you can't get around this, right? As the study size goes up, you do have more statistical power. You're able to better discriminate real effects from false effects, and so on. But you'll notice that the actual effect that it's regressing to here is 0.0. There is no effect. And yet, of course, you're going to get some, just due to variability, out here. And so if you only report the positive ones, you'll end up with this mysterious decline effect. Okay.